People hear the word infinity and they think physics has failed, because infinity feels like a red alarm light. It feels like the math is screaming, "This theory is broken." And sometimes it is. But sometimes infinity is not the end of the story. Sometimes infinity is just the universe telling you are asking the question in the wrong way. This is where QED, quantum electrodynamics, becomes one of the most shocking success stories in science. QED is the theory of how light and matter interact. Electrons, photons, the electromagnetic force, and it's famously one of the most accurate theories ever built. But here's the paradox. To compute even simple predictions in QED, the math tries to give you infinite answers. Not once, not as a rare mistake, constantly. And yet when you handle those infinities correctly, QED produces predictions that match experiments to ridiculous precision. So today we're going to answer a question that sounds impossible. How can a theory that generates infinities be the most accurate theory in physics? The answer is renormalization. Renormalization is often explained badly, so let's clean it up from the start. Renormalization is not sweeping infinities under the rug. It's not cheating. It's not inventing a trick to hide mistakes. Renormalization is something deeper. Renormalization is the process of connecting the symbols in your equations to the measurements in the real world, because the biggest mistake you can make in physics is thinking that the parameters written in your theory, like mass and charge, are automatically the same thing as what you measure in a lab. In QED, they are not. The electron charge you measure is not the raw charge you start with in the deepest equations. The electron mass you observe is not the raw mass the equations begin with. Why? Because the vacuum is not empty. In quantum field theory, empty space is not a dead background. It's active, it fluctuates, it polarizes, it reacts. An electron is never just an electron. It is surrounded by a cloud of quantum activity, virtual photons, virtual electron-positron pairs, constantly modifying what the electron looks like from the outside. So when you measure charge or mass, you are not measuring a bare object. You are measuring the object plus its interaction with the vacuum. That means the numbers in your equations aren't sacred. They are placeholders until you define them through measurement. Now here's the moment where infinity enters. When you compute the effect of that vacuum cloud, you often have to integrate over all possible energies, up to arbitrarily high energies, and that integral wants to blow up. Infinity. So QED forces you to face a brutal fact. If you try to describe nature down to arbitrarily small distances with no limits, the math can become infinite. But instead of giving up, physics asks, what if those infinities are telling us we have to redefine what we mean by mass and charge? That is the doorway to renormalization. To understand renormalization, we need one mental model. Imagine you're looking at an electron from far away. From that distance, you measure a certain electric charge. Now you move closer. You expect to measure the same charge because charge feels fundamental. But as you zoom in, you start seeing the vacuum respond. Pairs of virtual particles appear and disappear. The vacuum acts like a medium that can polarize. That polarization partially screens the electron's charge. So from far away, the electron can look like it has one charge value. From closer up, the effective charge can look slightly different. This is not philosophy. This is measurable. It's called running coupling. The effective strength of the electromagnetic interaction depends on the energy scale, or equivalently the distance scale at which you probe it. Now we can introduce the main characters of QED's infinities. Electron self-energy. The electron emits and reabsorbs a photon. This changes the electron's propagator and shifts the electron's mass. Vacuum polarization. A photon briefly turns into an electron-positron pair and back into a photon. This changes how electromagnetic forces behave at different distances. Vertex correction. The point where an electron interacts with a photon gets quantum corrections. This affects the effective charge. When you draw these as Feynman diagrams, they often include loops, and loop diagrams typically involve integrals that can diverge. So, what do? Step 1 is something called regularization. Regularization does not fix the infinity. It just makes the infinity manageable. It's like putting a fence around a wildfire so you can measure it. One crude way is a cutoff. You say, I won't integrate past some maximum energy. That replaces infinity with a large number. Another elegant way is dimensional regularization. You change the dimension of spacetime slightly so the integrals become well-defined, then you carefully take the limit back to 4 dimensions. Again, the point is not make it correct yet. The point is, stop the calculation from exploding so you can see the structure of the explosion. Once you regularize, you typically get something like a large finite piece plus a piece that blows up as the cutoff goes to infinity. Now, step 2 is renormalization itself. Here is the core idea, stated in the cleanest way. The bare parameters in the theory are not physical. The physical parameters are the ones you define through experiments. So you rewrite your theory so that measured mass is the mass that appears in predictions, measured charge is the charge that appears in predictions. That requires introducing counterterms. Counterterms are not magic. They are the difference between your bare parameters and the physical parameters you actually observe. When you do this consistently, the infinities cancel between loop corrections and counterterms, and the final predictions for measurable quantities become finite. This is the part that feels like a trick until you understand what the theory is really doing. Because the theory isn't saying the electron has infinite mass. The theory is saying, if you split the world into bare electron plus vacuum effects, each piece can be ill-defined by itself. But the observable thing, the full-dressed electron you actually measure, can be finite and well-defined. Renormalization is basically the mathematics of refusing to talk about unobservable pieces as if they were real objects. You only trust what the experiment can access. Now that might sound like a surrender, but it's actually scientific discipline. And it leads to predictions so accurate they look unreal.
Now let's talk about why QED became legendary. Precision. There is a famous number called the electron's anomalous magnetic moment, often written as G-2. If you compute the electron's magnetic behavior with a naive theory, you get one value. But when you include QED loop corrections, those same diagrams that threaten infinities, you get a slightly different value. That tiny correction matches experimental measurements with insane accuracy. And the reason we can calculate it is exactly because renormalization makes the predictions finite and stable. This is the point where you should pause and realize something important. Renormalization isn't a patch on a broken theory. It is a feature of how quantum field theories connect scales. Because the world behaves differently depending on how closely you look. When you probe at low energies, you see one effective description. When you probe at higher energies, you see corrections and new behaviors. Renormalization organizes those changes. And it forces you to abandon a comforting fantasy. The fantasy that the universe has one set of simple numbers that never change. In QED, the effective coupling changes with energy. The charge runs. The vacuum participates. Now let's address the big fear people have. Okay, but if you can cancel infinities by redefining things, couldn't you make any theory work? No. Renormalization is not a free permission slip. It only works cleanly for a special class of theories. Renormalizable theories. A renormalizable theory has a specific property. You only need a finite number of measured inputs to fix all the infinities. In QED, you can measure a few quantities, like the electron mass and charge, and the rest of the theory becomes predictive. If a theory is non-renormalizable in the old sense, you might need infinitely many measurements to fix infinitely many infinities, and then you lose predictive power. Now, modern physics has a more nuanced view. Non-renormalizable doesn't always mean useless. It can still be a valid effective theory at low energy. but the point remains. Renormalization doesn't make physics meaningless. It tells you which theories remain predictive as you change scale. This brings us to the deepest philosophy hidden inside renormalization. Physics is layered. At different scales, the best description of reality changes. You don't necessarily have one final equation that is equally simple at every level. Renormalization is the map that tells you how descriptions at one scale turn into descriptions at another. And in QED, that map is unbelievably successful. Now let's talk about the part that people misunderstand the most. Are the infinities real? When QED gives an infinite correction, is nature actually infinite? Or is this just the math? The honest answer is, the infinity is a signal that your theory is being pushed beyond the range where your assumptions remain valid. If you treat spacetime as perfectly smoothed down to arbitrarily small distances, the integrals can diverge. But in reality, at extremely high energies, new physics could appear. So you should not worship infinity as a real thing. You should treat it as a signpost. Your description needs to be handled carefully. Renormalization is the procedure that says, fine, we will define our theory through measurable quantities, and our predictions will remain finite within the regime where the theory works. Now, for the last part, we'll connect all of this back to Feynman's role and explain why this changed physics forever. So where does Feynman come in? Feynman didn't invent renormalization alone. This story includes Schwinger, Tomonaga, Dyson, and others. But Feynman did something that changed the entire culture of calculation. He turned these abstract corrections into a usable machine. Feynman diagrams made it possible to organize the series of contributions in QED. They made it clear which processes correct which quantities. And they made renormalization feel less like a mystical rescue and more like a controlled accounting system. You could literally look at the diagram and identify, this loop corrects the mass. This loop corrects the charge. This loop modifies the photon propagation. So instead of drowning in algebra, physicists could navigate the theory like engineers. And that's the key. QED became practical. Now let's wrap it up with one last clean picture. Think of bare electron as an idea you can write down but never isolate. The moment an electron exists in the real universe, it is interacting with fields. It is dressed by the vacuum. The quantities you measure, the ones you call the electron's mass and the electron's charge, are already dressed. They already include the effect of those fluctuations. So when your calculation tries to split that dressed object into a bare piece plus corrections, you can create infinities in the pieces. Renormalization tells you, stop treating the pieces as physically meaningful on their own. Use physical measurements to anchor the theory. Absorb the problematic parts into definitions. Keep the predictions for actual observables finite. That's not cheating. That's how measurement works in a universe where the vacuum is active. And this is why the phrase infinity in physics is misleading. The infinity doesn't appear in what you can actually measure. It appears in the internal bookkeeping you create when you push the theory to extremes. Renormalization is the discipline of making sure your bookkeeping never pretends to be reality. And when you do it right, QED becomes a masterpiece, a theory that produces the most accurate numbers humanity has ever extracted from nature. So here's the final takeaway. Renormalization isn't a hack. It's the rule book for how physics changes with scale. It tells you that empty space isn't empty. It tells you that measured constants aren't always constant at every resolution. And it tells you why the most terrifying word in mathematics, infinity, can sometimes be the start of deeper understanding instead of the end. If you want to continue this series, the perfect next video is how Feynman diagrams actually calculate probabilities. Because once you understand amplitudes, paths, and renormalization, the diagrams stop looking like art and start looking like code.